So Lucian, can you confirm for me that we got transferred to the webinar and we're going now?
Yes, so the attendees list is populating, so.
Okay, perfect. So I'm probably going to give one more minute and then we can I'll introduce our speaker for day 3 here. Was the clock set back when you were at Berkeley, Ivan? Did everything start 5 minutes afterwards or whatever?
I don't remember that, but
okay.
Of course that was 30 years ago when they used to have a show. Yeah.
Maybe it was considered not cool to look at a clock in the first place.
Yeah, it was maybe, but I think that's a 21st century thing. Yeah. I'm a 20th century guy, you know.
Awesome. Okay. So welcome everyone to the 3rd day of our spring school on open quantum systems. Today we have a real treat for you. We have Ivan Deutsch from the University of New Mexico, and he's going to be talking today about continuous quantum measurement and quantum trajectories. But I want to give you a little bit of a reminder of all the wonderful things that Ivan has done in his career. So Ivan graduated from MIT with his bachelor's degree in 1987. And then he went to Berkeley and he worked on, for his thesis project, he worked on 2 photon bound states. And if you think about what that means, you're talking about a situation where you've effectively made an interaction between photons. So I like to think that Ivan invented the lightsaber sometime around the early 90s there at Berkeley. And then he went on to a couple of postdoctoral appointments, but the one that I think was sort of the big one was he was at NIST after that. And then in 1995, he joined the faculty at University of New Mexico, where he has been ever since. He's won a number of awards. He's the 4-time recipient of the Physics and Astronomy Excellence in Teaching Award, which is one of the reasons that we were really excited to get him here. Not that he won the award, of course, but that we know he deserves such awards because he's such a good instructor and a good communicator of science. He also very recently won the APS 5 Sigma Award for Science Policy Advocacy. So he's a wonderful citizen for all of us, and he's out there on Capitol Hill doing the good work to try to advocate for good science policy decisions. I would say probably the thing that I know Ivan the most for is his fearlessness as a theorist. He's the type of person who will just jump right in and he says, okay, now I need to know how to calculate electronic structure and scattering between atoms. And he'll just dive in and do it, even though he doesn't necessarily have training in that particular subfield. He's just broadly knowledgeable and fearless. He has a lot of originality. His probably most notable contribution in the past 25 years or so is the 1999 Physical Review Letters paper on quantum logic gates and optical lattices. So if you think about all the exciting things going on with neutral atom quantum computing, this was the first real kind of blueprint for how you would do quantum computing with neutral atoms. And I think that you could really point to that as being something that kind of got the field going. And now it is on a very steep trajectory. And that is due in no small part to the work of Ivan with Carl Caves and Paul Jessen as well on that work. I mentioned that he's a theorist. He has a deep understanding of physics. Before I hand it over to Ivan, I will also say he's the only quantum information scientist I've ever heard to sincerely express annoyance because H-bar is too big. So without further ado, I give you Ivan Deutsch. Take it away.
Oh, Wes, thanks. Yeah, thanks for thoroughly embarrassing me. I appreciate it very much. If someone wants to ask me that question about H-bar, we'll talk about it during the question and answer. I'm happy. That'd be fun to talk about. Very good. Well, welcome everybody. Although I can't see you out there in webinar land, I hope sometime soon we'll get to cross paths in real life. So let me get going here by sharing the screen. And let's see. So does everybody see the PowerPoint now? You guys see it? All right. So we're going to do a combination of some slides just to get started, and then the digital whiteboard on the iPad. And of course, I guess there is a way in which people ask questions through the Q&A, and we have some monitors here who will be looking at the questions and interrupting me at any time. So I encourage you to please, put those questions in and make this as best as possible a conversation. So let me get this into that mode. Are you seeing the presentation mode or the actual screen? Is it in good? Does it look good for you guys?
Yep.
Because I have two monitors. Okay, good. Because I can't tell whether you're seeing the presentation mode or the wrong screen. Okay, good. So let's get started. We're going to get started by saying a few words about quantum measurement theory, because there is an intimate relationship between quantum measurement theory and the theory of open quantum systems, which is the subject of this school. So let's begin by thinking about, how most of us, at least, back in olden days, thought about what a quantum measurement was, how we were taught about quantum measurement. So we have some quantum system, like an atom, and it's in some quantum state, which is in some superposition of some eigenstates of some observable. And we want to do a measurement on that system. We want to measure that observable. So we wheel out some meter, the classical meter. I don't know what this meter is. It was what I found in Google Images, but it's the thing that measures the observable O. And what we are kind of taught, okay, if we do a measurement on this system, then the meter will read, the position on the meter will read something that is proportional to the eigenvalue of the observable that we want to measure. And when we find that eigenvalue, then the system collapses, right? You project the system onto the eigenvector corresponding to that eigenvalue, and the state after the measurement collapses onto the eigenvector corresponding to that eigenvalue. Now, of course, this is magic, and we have no idea how to describe this as some physical effect in this context. There was the mind of Bohr, whatever that was, that had this idea about the classical apparatus is the way in which the measurement value emerged. By the way, of course, this measurement occurs randomly. Which outcome we're going to get, M, is not known a priori. We can only predict the probability with which we will see M, and that's given by the Born rule, right? The probability amplitude squared tells us the probability of that outcome. Now, von Neumann tried in some way to bring the measurement process into the quantum world. And through that, actually, that paradigm, the more modern perspective on quantum measurement emerges. Of course, it doesn't really solve the so-called measurement problem, but it gives us a little bit of inching towards that. So now the idea is, instead of thinking about my apparatus, do you see my cursor, by the way? Yeah, good. We were going to treat the meter now as a quantum mechanical device that we have prepared. We think about the position of the meter as being in some wave packet, okay? And so there's some wave function that describes where the meter is. And it's prepared in some wave packet, we've calibrated it, and it's localized at what we're calling 0. And then there is a quantum mechanical interaction between the quantum system and the quantum meter. And that interaction is described by some kind of Hamiltonian. and there is some unitary evolution that describes the joint evolution of the system and the meter, sometimes called the ancilla, okay? And what the interaction is set up to do is that it displaces the meter by an amount proportional to the value of the observable of the system that we want to measure. And everyone remembers that the generator of displacements is momentum, right? So this operator will displace the meter by an amount proportional to the observable with some coupling constant that's called chi here. So here we are, we wheeled out the meter, it's uncorrelated with the system. Now we let them interact for some amount of time, okay? And that's what happens. And if I plug in this superposition state of the state of the system, then I can replace the operator O with the eigenvalue M, because M are the eigenvectors of the observable O. And so I've done that, and now I can apply this operator to the state of the ancilla, or the meter. And as I said, what it does is it displaces the meter, which was localized at 0, now it's localized some amount away, okay? All right, and so here's an example. Let's suppose that we prepared the system in a superposition of two of the eigenvectors of O, M1 and M0, okay? So when I do that, after the interaction, I have this correlated state where the joint state of the system and the ancilla is, okay, there's this part of the state where the atom is in M0, and in that case, nothing happens, or it's displaced by, I'll call that amount 0. So it's just sitting there. Or there is some probability amplitude that the atom was in M1, in which case the wave packet is displaced by some amount 1, okay? And so then by just looking at whether the meter is here or here, I will get information about whether the atom was in M1 or M0. And when I do that, in this case, the interaction was pretty good, and these two wave packets are sufficiently separated from one another compared to their uncertainty that when I see the wave packet here, it's completely orthogonal to the state 0, in which case, when I find the meter in state 0, I will collapse the atom into state M0. And if I find it in 1, I will collapse to M1. In other words, the meter is entangled with the atom. And when I learn about the meter, there is spooky action at a distance, which collapses the state of the atom, right? And that's the way in which we can imagine we both learn information and do the collapse. Now, of course, I've moved, there is me, the observer, looking at where that is. So there's still the issue of the collapse is not solved by this. Nothing collapsed here until I looked and saw whether the meter was in 0 or 1, but never mind that for now. All right. Oh, and of course, the post-measurement state of the atom I can get by projecting the joint state of the system, which is this, onto whichever outcome I find for the meter. When I find an outcome of the meter, I do the partial projection onto that state of the meter, and the remainder is the state of the atom. In this case, that again was a projective measurement. Okay, so far so good. So now, I'm sorry.
Can you hear me? There is a question in the Q&A.
Okay, yes.
So the question is it possible to find the meter in a particular spatial superposition state, collapsing the atom into a superposition itself?
Absolutely. So if I could rig up a measurement that I would do on the meter that does not give me information about whether it's here or here, then I will not do that measurement. And we're going to see that a little bit more detail soon. So this is in the case where I actually I do a position measurement, which is I try to look where the meter is. And in doing so, I would, in that case, collapse the atom into one of the other states because these two are orthogonal. But if I were to do a measurement that did not resolve this different, then I would retain that superposition, which leads me to the next slide. So here's a case where the wave packet wasn't sufficiently localized initially, okay? And there was a lot of quantum noise, if you like, on the meter, in which case the displacement that I get leaves these two states with a finite overlap. And so if I find the meter here, I can't really tell for sure whether that corresponds to this wave packet or that wave packet. And in that case, I won't completely distinguish the two cases, and I won't collapse the wave function into the state M0 or M1. It is not a projective measurement. It's a more generalized class of measurements, of which is what we would call a Povm, which we'll say, maybe I'll just say a few more words about it as we go on. So here, what we see is that this is what we might call a weak measurement, not to be confused with the weak value, which are a whole nother set of stories of the Haronoff weak value. No. This is just a general statement. In fact, no measurement we do in the laboratory is ever a perfect projective measurement. All measurements have some noise on them, and so really should be described more generally of the class that I'm discussing right now. Okay, now, importantly, and this connects to the first lecture that I think everyone heard from Daniel Ladar, this connects to the idea of the Kraus operators of open quantum systems, which is the connection we will make as we continue a bit. So, as before, if I want to know what is the post-measurement state of the atom, after it's entangled with the meter, and I do a measurement of the position of the meter, I ask, where are you on this dial? To get that state, the state of the atom, conditioned on having found the meter in position X, is what I get when I project this joint state of the system and the ancilla onto the position X of the ancilla. And that is not generally a projection onto the value X. It is a more general thing, which is what we call a Kraus operator or a measurement operator. I think Daniel called this M in his notes. I'm calling it K for Kraus, okay? So this is going to be an important object. It is the important object for understanding everything about measurements and open quantum systems, is the Kraus operator, okay? And the Kraus operator in this case was what we got on the joint state, the initial joint state of the system ancilla after they became entangled, and then I did a measurement on the ancilla, in this case, the position measurement, okay? And the Kraus operator here, thus, is the partial matrix element between the initial state of the ancilla, which was the initial wave packet, the entangling interaction, and then the measurement I do. This is not a number. This is an operator. I'm going to ask a question. Why is this still an operator? Anybody in the chat? I mean, I thought, you know, when you take a matrix element, why am I calling this an operator and not a number? Anybody in the chat want to weigh in? Wow, okay. Maybe the reason is that this is a joint. This operator acts on both the system and the ancilla. And I'm only taking the matrix element with respect to the ancilla part. So this remains an operator that acts on the system, on the atom. So this is an operator that acts on the atom, okay? And the probability of finding that, just as before, by the Born rule, is the square of the unnormalized state, which if I write that out, given this state, is this expectation value. And this operator, K dagger K, I'm calling E. This is a more generalized form of a measurement that I mentioned earlier. This is what's known as a positive operator valued measure. That's a very heavy-handed name. We just call them POVMs. No one calls them positive operator valued measures anymore. As I like to say, it's like the artist formerly known as Prince. And we just call it the POVM. And it's called, I mean, so what it's called a POVM because these elements are positive operators and they're positive, thus their expectation values are positive numbers. They tell us the probability of a given measurement outcome. They're called a POVM because they're complete in the sense here, X is a continuous variable. So if I integrate over all possible values of X, this is a resolution of the identity. And this is a measure, you know, in integral land, but it's an operator valued measure. It's also positive, and thus it's a positive operator valued measure. Okay. All right. Very good. Any questions so far? I'm going to pause here for a moment because we're going to switch to the digital whiteboard. Are we okay?
There are no questions.
Okay, very good. All right, let me stop the share. And I'm going to share my screen here on the iPad. All right. Very good. All right, I need to see if I can make this work. All right, let me.
Ivan, there is a single question.
Yeah, please go ahead.
So the question is, how does the POVM reduce to a simple measurement?
Yeah, so an example of a POVM is a projective measurement. Maybe let me share my screen and I can just maybe say a few things here. So let's get this going. If I can rotate this thing, rotate. All right. So just quickly, what we were saying is that, you know, a POVM was a set of operators that was positive such that it's a resolution of the identity. This, I'm writing it here as a discrete sum over a discrete set of outcomes, but it also could be a continuous alpha-like position, okay? So an example is a projective measurement. This is the kind we all learn about in initial quantum mechanics, where the POVM elements are in that case just the projectors onto the eigenvector. So let's say, let me call this instead. Let me call it, as we were in the screen there, let's call it M. So I can say in this case that the POVM elements here are projectors onto the eigenvectors of the observable. This is a POVM because if I look at the sum, in this case, over, this is a complete set, this is the kind of thing we all know about in the way we're typically taught quantum mechanics. That is a measurement. So this is the simple measurement, but there are more generalized measurements whose POVM elements are not projections. And those do not necessarily fully collapse the system onto one of the eigenvectors. Those are the more generalized set of measurements and the ones that actually occur in the laboratory. All right, so now I want to connect this to the notion of open quantum systems, okay? And the way I want to do that is to say the following. So now I have my quantum system like the atom that we were just talking about. Here it is. And instead of thinking about the ancilla as being that crazy device I rolled out, my ancilla is going to be the quantum environment. So in an open quantum system, what we know is that the system is coupled to the environment and typically will undergo decoherence or dissipation, loss of information. How is that happening? Well, it's happening because the system and the environment are coupled together. Say, if the whole universe that's not the system is the environment, there's some unitary interaction that couples the two together, right? And in doing so, the system will become entangled with the environment. So we can think about, in the same way that we said before, the environment is continuously monitoring the system. You can say that the environment is measuring the system all the time. Now, if we don't know that measurement outcome, then of course, we have to trace over the environment, and the system, as you learned in your first lecture with Daniel Ladar, will undergo a completely positive map, will become a mixed state, okay? But we can think about this in a so-called measurement model in the same way that we had the meter, and then we looked at the meter in some basis. Let me call the basis that I'm going to look at the meter. This is the basis of the environment. This is going to be me doing some kind of measurement on the environment, okay? If I were to do that, what happens? Well, here's what we learned in the first lecture. What we know in this situation is that the state of the system, we have to trace over the environment of the joint interaction between the system and the environment. So this is the output state. This is the input state. And we prepare the environment in some ancilla state. This is the state of the environment before the interaction, and then they get coupled together. And as we learned in the first lecture, this is a CP map. With Kraus operators, came in. Okay. So this operation is what we called a CP map. And the Kraus operators here are I do a measurement of the environment just like we did before in some basis. I'm calling mu here. There's the joint interaction acting on the initial state of the bacillus. So this was like the initial wave packet of the meter. This is the entangling interaction, and this is the final measurement, just like we had before. Okay. Now, here's a very important point. The important point here is that this, we said, was tracing over the environment, right? But what if we didn't trace over the environment? What if we actually was able somehow to do a measurement of the environment, and we found in whatever measurement we did the outcome mu? What would be the post-measurement state of the system conditioned on that? Well, what we just saw in the case of the meter, if we actually found that outcome mu, then what I have to do is apply the Kraus operator to the state. Here I'm saying it's in a slightly more generalized way than I did before. We used pure states before, now I'm using more general states. And then I have to normalize it. I do the trace of this thing over that. Okay. That would be the state of the system if I found that measurement outcome mu. And if I do that trace on the denominator, that's the trace of this, but I can use the cyclic property of trace to rearrange that, write it like this. This we recognize as the Povm element we just talked about. And this thus is the probability. I'm sorry, my handwriting is so terrible. I wish it were better, but you know, what are you going to do? So let me just write this out. So the post-measurement state here is that if I were to have measured and found the outcome mu, all right? However, if I don't know what that measurement is, then what I should do is just average over the measurement outcomes weighted by the probability that I saw that measurement. So this output state, the one that involves the trace over here, this guy, can be rewritten with that. As you see this thing, I can rewrite it in the following way. The output state, after I interact with the environment, is the sum over all possible values mu, p mu, rho mu. Do you see that? Does everyone see that? That if I put these two guys together, I get this? Okay. So this is an important point here. What we can say here is we have a picture of the open quantum system. Which we call the measurement model. And the measurement model says the following. It says the environment is continuously measuring the system if I don't have access to that outcome, I average over it. And that is equivalent to tracing out the environment. Okay. Anybody have any questions about that? Okay, that's our first important lesson that we're going to take forward. Okay, so let's move forward. So now, in particular, if I want to look at the dynamics of an open quantum system, okay. So let's, for example, say that I had some, at initial time, or at some time t, my state is pure. Okay. What would be the state at I step forward in time some amount dt? Well, it's not necessarily going to be pure unless I do a measurement on the system, a measurement on the environment, which tells me the value mu. The post-measurement state of the system conditioned on measuring mu would be, I would apply the Kraus operator that is corresponding to that outcome, and then I would renormalize it. Okay, where p mu here is the norm squared of this. This would be the dynamics of the pure state if I were to, this is in the case where I look at the environment. Okay, but if I don't look at the environment, then I have to average over this, right? Which would say that my state of my system would be in general mixed. So I would have to weight each of these guys by these guys. That would be the open quantum system dynamics corresponding to averaging over the measurement outcomes. Which is equivalent to tracing out the environment. And in this case, when I plug that in, that's equal to the sum over mu, k mu, k mu dagger. Now, in this case, I should have emphasized that these k mu's are functions of the differential, they might be functions of time, but they're functions of whatever the dt is, right? Because that's the thing that propagates me forward in a time dt. So just in words, again, to emphasize what's going on here. The system and the environment interact for some interval dt. the environment contains information about the system. The environment and the system are entangled. If I trace that out, I would generally cause decoherence, and the purity of the state would decrease. It would decohere. I would lose coherence. I can understand that as different possible measurement outcomes that I see in the environment, which would correspond to different preparations of the system conditioned on that, okay? But since I don't have access to it, I have to average over them with some probabilities p sub mu, okay? Any questions? We're okay? All right, very good. All right, so let's look at an example then. My example here, let's think about a two-level atom. Was there a question?
So there was a question related to this point, which is whether the Kraus operators form a group.
I'm sorry, Pablo, can you repeat that? Somehow the volume is not very high.
There is a question, which is whether the Kraus operators form a group.
Oh, yeah. No, because so this is a very good question. The Kraus operators are not unitary operators. Okay. You might say there's a semi-group in this case because they're not invertible. So let me just maybe say, you know, if I were to think about a closed system, then my system would evolve according to a unitary evolution like that, right? And the Kraus map written over here is a generalization of unitary. It looks similar, but it's not the same, right? The unitary operators, of course, form a group because this is reversible. This is irreversible. So one of the hallmarks, of course, of open quantum system dynamics is that there's generally an arrow of time. And so there will be, it will be irreversible and thus not invertible. And because it's not invertible, they don't form a group, okay? Very good. All right. But I do want to make sure everybody understands or has any questions of this important point about the relationship between measurement and open quantum system dynamics. That is to say, mathematically and conceptually, we can think about the open quantum system dynamics as the environment is constantly measuring the system, but not telling us the result. Now, the environment doesn't necessarily do a projective measurement. It doesn't generally a weak measurement, generally a measurement that does not instantaneously project the system onto one of its eigenstates, but over time, it might accumulate to do so, okay? So this is an important connection between measurement theory and open quantum system dynamics. All right. Let me continue then and talk about this example of the two-level atom. Decaying in the vacuum. All right, so let's imagine we have an atom. We call it a two-level atom because we're only worrying about two levels, the excited state and a ground state. Okay, the atom is in the excited state, then we know at some time it will spontaneously decay, and there is a spontaneous emission rate, gamma, which is the 1 over the natural lifetime, say, okay? Now, why does the atom decay? Because the atom, in this case, is the system, and the environment is the electromagnetic field, which is quantum, okay? And so we initially have some state of the atom. For example, we might have prepared it in some superposition of ground and excited state. And initially, the atom is in the vacuum, say, relative to optical photons at room temperature. There's no black body radiation. I could just treat it as a 0 temperature vacuum. And these two things become entangled with one another. And over time, the atom will spontaneously emit, right? And that is open quantum systems dynamics. That is irreversible. And of course, eventually, over a long time, the system decays to the ground state. And I've lost all information about whether or not this is what the initial superposition, I cannot reverse that. So this is a nice example of irreversible evolution, right? So what is the dynamics of this? Well, we're going to see that this dynamics is describable by the kind of Kraus map that we discussed a moment ago. But a more familiar form, at least to most of us, and I don't know whether Daniel Ladar got to this in his lectures or not, but I think they're in his notes. And of course, everybody's done their homework and read all the notes beforehand. So I'm going to assume you've done that. And we typically describe the evolution through what we call the master equation. So the master equation is the generalization of the Schrodinger equation, which tells us how the state of the system, the density operator of the atom, evolves in time, okay? And if there was no coupling to the vacuum, there would be just Hamiltonian evolution. And that Hamiltonian evolution is given by the commutator with the density matrix, with the Hamiltonian of the atom. And then there is a dissipative term. I'll call it L rho, or an open, the part that has to do with the open quantum system. And that L here is minus gamma over 2, sigma plus sigma minus rho plus rho sigma plus sigma minus plus gamma sigma minus rho sigma plus, where I'm treating the atom as a two-level atom with a pseudo spin where sigma plus takes me from the ground state to the excited state, and sigma minus is the conjugate, which takes me from the excited state to the ground state, okay? This is the master equation that describes the evolution of the state of the atom when it is interacting with the electromagnetic vacuum, okay, at 0 temperature. And this has what we call the Lindblad form. The Lindblad form of the master equation generally is written in terms of there's a Hamiltonian for the system, and then the dissipative part can be written as minus a half, I'll call it L dagger L with rho plus L rho L dagger, where this is the anti-commutator. And the L's here is called the jump operator, or the Lindblad jump operator, for reasons that will become clearer in a moment, okay? They're the Lindblad operators or the jump operators. So we see that our equation above over here is of the Lindblad form. Oops. This equation is of the Lindblad form, where in this case, the jump operator is given by the square root of the spontaneous emission rate times the lowering operator that takes the atom from the excited state to the ground state. So that's my jump operator. And it corresponds to a quantum jump happening that takes me from the excited state to the ground state. Okay. All right. So let's see. Right. The Hamiltonian of the atom in this case is simple. Since I have two levels, I can expand it in its eigenstates. It's the energy of the excited state plus the energy of the ground state. And if I just set this to be 0, then this is equal to h bar times the energy difference, the Bohr frequency associated with that transition, okay? So the Bohr frequency is just the energy difference divided by h bar. So that's the simple Hamiltonian of the atom. And I'll write that as h bar omega Eg sigma plus, sigma minus, right? Because sigma plus times sigma minus, you can easily convince yourself is equal to the projector onto the excited state. Very good. So now I can rewrite the master equation in the following way. I'm going to rewrite it as minus I over h bar, something I'm going to call h effective rho, minus rho h effective dagger, plus gamma sigma minus rho sigma plus. I'm noticing all kinds of typos in my distributed notes, which I must now correct. Okay. Now, what is this h effective? This h effective is equal to the Hamiltonian of the atom with an imaginary part, minus I h bar gamma over 2 times sigma plus sigma minus. Okay. I ask you to try for yourself to show that when you plug this in to this expression, you get the master equation we had before. Okay. That is to say, the master equation that we had before, you see, had this term over here with these minus sigma plus and sigma minus terms. They are part of the imaginary part of the evolution, such that when you put that all together, you get this. Okay. Very good. So what can we say about this imaginary part? Let's just write it out again. What we see, this is just the projector onto the excited state. If I plug in here, this was h bar omega Eg, then this is h bar omega Eg minus I gamma over 2 times the projector onto the excited state. That is the effective Hamiltonian. This is non-Hermitian. This effective Hamiltonian is not a Hermitian operator. It has an anti-Hermitian part, or an imaginary part, because of this I. But notice what it is. It's exactly what we, if we didn't know anything about open quantum systems, and we just say, oh, there is dissipation, there is a damping coefficient, the oscillation, as we know of a simple harmonic oscillator, in the presence of friction will damp. And the way we typically do that in classical dynamics is that we could just add an imaginary part to the frequency. And that imaginary part tells me something about the damping of the oscillation. Here, the superposition of ground and excited state of the atom would be damped at the rate that depends on the spontaneous emission. And so we've added an imaginary part to the energy of the metastable state, or the excited state, now has an imaginary part, which is related to the lifetime or the spontaneous emission rate, okay? So if we were to just be naive for a moment and say, okay, let's say that the system just evolved according to the effective Hamiltonian. How would it evolve? Let's suppose that I started the system in some pure state at time equals 0 in a superposition of some amount of ground and some amount of excited. And I said, all right, psi of t is the time evolution, but instead of through the Hamiltonian, now I'm just going to add an imaginary part to the energy that corresponds to the damping rate of this and act that. This is a generalization of the Schrodinger evolution, but now with an imaginary part to that, okay? What that would do, I'm going to call this psi tilde for reasons that'll be clear in a moment. If I take that with this guy, it does nothing to the ground state. But the excited state now has the phase, but it also has a decay term, right? And so the probability to be in the excited state at a later time, by the usual way we would calculate it, that amplitude squared is the initial probability e to the minus gamma t. So the probability to be in the excited state decays as expected. It decays at the rate of the spontaneous emission, okay? So this effective Hamiltonian takes into account the fact that the excited state is not infinitely long-lived and will decay to the ground state. But notice in this problem that by the effective Hamiltonian does not replenish the population in the ground state. The population in the ground state at all times was what it was at the initial time. Okay, and in fact, what we see is that the norm of this vector decreases with time. It's equal to 1, it's the ground state plus the excited state. And if the initial probability was conserved, but now at a later time, oops, it has decreased. So the effective Hamiltonian, because it is not Hermitian, does not preserve the probability. It accounts for the fact that the excited state decays, but it does not account for the fact that after the state decays, population should be refed into the ground state, okay? But the master equation does that, because remember what we had in the master equation here. So this evolution, this part of the evolution was due to the effective Hamiltonian. What does this evolution do? Well, that evolution, if I write it out in terms of the raising and lowering operators, the lowering operator is this, and the raising operator is that, okay? So, what I see is that this term is equal to the population in the excited state. That's this guy over here. This is the population in the excited state. Oops. Times G. So importantly, this term will evolve the state of the system in a way that puts population back in the ground state by a rate that depends on the spontaneous emission rate times the probability of being in the excited state. But the effective Hamiltonian part doesn't do that. And we thus see that there are two kinds of evolution that are occurring in this master equation: the decay term and the replenishing term. The decay term that we had discussed over here, we think this we can look at as deterministic. It's evolving according to time. But the replenishing term is a quantum jump. That is stochastic. Okay, so there's a combination of those things happening in the master equation. Let's connect this now to what we discussed at the beginning of this lecture in the context of the Kraus map. Okay, so let's rewrite our master equation. I'm going to write the master equation again. So let me do that. We said that d rho dt is equal to minus I over h bar, the effective Hamiltonian times rho, minus rho h effective dagger, plus gamma sigma minus rho sigma plus as we had, okay? So now I can integrate this over a short interval dt. And when I do that integral, I get what I simply get is the following. This is this is rho of t plus d rho dt dt, which is equal to So first order in dt, 1 minus I h bar h effective dt times rho 1 plus I over h bar h effective dt plus gamma sigma or dt sigma minus rho sigma plus. Okay. And what I thus see is the following. Rho of t plus dt has the form of a Kraus map. It's a Kraus map with two Kraus operators that I'm going to call K0 and K1. Where K0 is 1 minus I h effective over h bar dt, which is approximately e to the minus I h effective dt. And K1 is equal to the square root of gamma dt times sigma minus. Okay. I want to pause there to just say what we've just shown. We've said thus that the evolution of the master equation over a time dt is a map. It's a Kraus map with Kraus operators K0 and K1. Okay, where these are the two Kraus operators. Now, as we described in the beginning part of our discussion, any Kraus map corresponds to a measurement model. So what is the measurement model here? Well, the K1 is a jump and K0 is a no jump. If we don't do a jump, the system evolves in the deterministic way. If we do a jump, we go from the excited state to the ground state. There are two different cases here that correspond to those two different kinds of evolution. What measurements do they correspond to? Does anyone have a clue? So again, I want to remind you what we're talking about here. What we're talking about is a two-level atom. And the environment is the quantum mechanical vacuum, right? A open quantum system dynamic can correspond to me doing some kind of measurement on the electromagnetic field, the quantized electromagnetic field. And because the field is correlated with the atom, by measuring the field, I learned something about the atom. So what do these two post-Kraus operators, what measurement do they correspond to? Okay, does anyone have I see seeing or not seeing the photon? Exactly. So the measurement that I'm doing in this case is I have a detector which is looking for photons. The one in the 0, 1 corresponds to the situation where I measure 1 photon, and 0 corresponds to no photons. Okay, so depending at every interval, I can ask photon, no photon, photon, no photon. Depending upon whether I see a photon or not, I should apply the appropriate Kraus map that updates the state conditioned on that measurement outcome. Okay. Now, I want to say a few more words about the no jump condition, because it's quite interesting what happens. So let me maybe before I do that, I'm looking at my notes here. Let's just try to get at this a little bit in more detail, how this kind of Kraus map works. So let's suppose at some time t, the state of the system is pure. Okay. Then the state of the system at some later time would be the following. Well, if I didn't see a jump, then the state of the system would become the no jump state conditioned. Okay, let me write it this way. The state of the system at a time dt later, conditioned on the outcome u, we said is k mu acting on the state renormalized, where p mu is equal to the expectation value of k dagger k. Okay. The state of the system, if I don't know the measurement result, is going to be equal to the weighted sum of these. So I'm going to have a P0 times psi 0. Let me call this size 0 or mu to get the notation the same. T plus dt. Plus P1 psi 1 t plus dt. Psi 1 t plus dt. Just as we had before. So this is the no jump preparation, and this is the preparation of the state in cases that I jumped. If I don't actually retain that measurement outcome, then I need to average over those outcomes weighted by the probability of having seen that, okay? And this leads us thus to a way in which I can do numerically this update rule. I can do this through a process which is sometimes known as quantum Monte Carlo wave function algorithm. All right, so how would I do that? Well, what I would say, I would do this in the following way. I want to simulate this kind of evolution with two possible, in each little time interval dt, there are two possibilities. Either the atom underwent a quantum jump or it didn't. I'm going to roll the dice somehow to simulate with random numbers, hence the term Monte Carlo, these two possibilities. And depending upon which possibility happens, I will apply the appropriate Kraus operator to update the state conditioned on that measurement outcome. So let's do it in the following way, okay? So the first thing I would do is I would, in the time interval dt, I would calculate on the computer the probability of a jump. Okay, so my little probability, the probability that the jump happens in the time interval dt, we said was equal to, for one was equal to, that's the probability of a jump, is the probability of P1, which is equal to K1 dagger K1, and K1 was equal to, if we remember, the square root of gamma dt, so it's gamma dt times sigma plus sigma minus, because I remind you here that we said that K1 was equal to the square root of dt times the jump operator, which is the square root of gamma dt sigma minus. Okay, so that's the probability of the jump. If we just simplify this a bit, this is the projection onto the excited state. The probability of undergoing a jump in that interval thus is equal to gamma times the square of this amplitude dt, which is just the probability to be in the excited state. So that's the probability that I will undergo a jump. Okay, so that's the first thing I do. Okay, then I simulate this with a random number generator. Okay, so that is to say, what I'm going to do is I'm going to pick a random number uniformly between 0 and 1. Oops. Pick some epsilon, and then if you know, epsilon is less than this probability that I just calculated, then I do the jump. Okay. Otherwise, okay. So now I say, okay, if this falls in that region, if epsilon is less than that, then I jump. Which is to say, I take the state at time t, I apply the jump operator to it, and renormalize. All right, so that's equal to applying this guy to the state and renormalize. In this case, that's just the ground state. But in general, it'd be something else for a more general master equation. Okay. Else, don't jump. If I don't jump, then the state of the system, I should maybe write it in a slightly different way. K1, it's the same thing because K1 is just proportional to the, is just proportional to the L, right? That's the same thing. Else don't jump. If I don't jump, then I apply K0 because that is the measurement outcome of not seeing a photon. And the measurement outcome of not seeing a photon means that measurement occurred, and I have to update the state conditioned on that measurement outcome. And that is equal to applying the effective Hamiltonian evolution over the time interval dt to the state and renormalizing, okay? And then I have the state at the later time, depending upon which of these outcomes happen, and then I rinse and repeat. Meaning that now I do the next interval, I roll the dice again, see if a jump happens, I ask jump, no jump. I simulate that with rolling the dice on the computer. If my epsilon comes up right and it jumps, I apply the jump operator, else I apply the no jump and do it again and again. And what we see in this process is that this state evolves stochastically over time. That stochastic evolution is what we now call, it was a term coined by Howard Carmichael back in the day, a quantum trajectory. A quantum trajectory is the following. A quantum trajectory is the evolution of the state conditioned on continuous measurement. Okay. So the point here is that in the Schrödinger equation, the state evolves deterministically according to Hamiltonian. But when we have, so let me maybe draw a little picture here. When we have the system here, it has its own Hamiltonian, and in the presence of that, it would evolve. But because it's coupled to the environment, and we're measuring the environment with these two outcomes, the back action that we see through this process gives us a random collapse or a random evolution onto the state. Okay, now the final point is that that's not the open quantum system dynamics, because the open quantum system dynamics is the density matrix. It's not the quantum trajectory. But if I average over quantum trajectories, then I get the open quantum system dynamics. And the averaging happens with exactly the right statistics, because I rolled the dice in a way that simulated the probabilities that occurred for jump versus no jump. So the way that I would get the density matrix is I would run my quantum trajectory calculation over and over and over again. And I would take the limit, hopefully for a number of trajectories, and average over all of the trajectories, where the I here represents the ith time I ran my quantum trajectory. Each of these each I represents a different quantum trajectory. Okay. And if I were to simulate this on the computer, I would have to run this trajectory over and over and over again. eventually it would converge. It's, you know, what it's like having in the experiment n atoms. I have to actually average all over all the atoms which undergo the particular evolution. So I'm going to have error bars that depend on, in my simulations, depends on the number of trajectories I have in the system. Okay. Let me pause here for questions. We're going to take a break soon, I think, because I think we probably need one. But let me pause here for questions.
Great. Yeah, so we have a few questions lined up. Perhaps the first one is the most recent one, but it's related to this, which is how is this method differ from directly solving the master equation with super operator methods?
Excellent. Good question. So there are two things about it. So we can directly integrate the master equation. The master equation is a differential equation. It's a deterministic equation. We can integrate it, right? And as I think was suggested, I can write rho as I can vectorize the matrix. This is remember, if I have a d-dimensional Hilbert space, then my density matrix is a d by d matrix. It has d squared entries. Okay, or elements. So I can think about vectorizing this as a d squared vector, in which case, as was suggested in the language of the question, I can think about my evolution as some kind of super operator, super operator acting on the vector, okay? And this is a d squared by d squared matrix that acts on the d squared vector. So in principle, we can do that, and we often do that, but it takes d squared, it takes more memory. So one of the original reasons this quantum Monte Carlo method was developed was from the point of view of numerics. Back in the early 1990s, when this was first developed, when memory was extremely expensive, you couldn't get much RAM. It would be very hard if your dimension was very big. It would be much better. The quantum trajectory method requires evolution of pure states. And the pure states only have d elements. So if memory is your problem, then quantum trajectories are a good numerical solution because they take up less memory. But of course, there's more time. If time is of the essence, then you're in trouble because you have to run the trajectory method, because an individual trajectory does not solve the master equation. You have to do many trajectories, and ultimately you want to do as many as possible depending on the statistics that you need in order to obtain the right ensemble average, which corresponds to tracing out the environment. So I would say two things about this. One is there's a difference in the numerics of what you do, but probably more importantly, the quantum trajectory method is a conceptual method which teaches us something about the nature of open quantum systems and its relationship to measurement. But in addition, as we will see, maybe depending on where we get today, or you can read about more in the notes to follow, suppose we actually do this measurement. Well, then we actually realize a quantum trajectory. And that's itself a very interesting thing. It's the way in which we can induce back action on the system, control the system through the measurement we do on the external environment. And in fact, we might even feed back that measurement result. And that's fun. That's called quantum feedback. So there's all kinds of reasons for studying this quantum trajectory method, not just from the point of view of its numerical efficacy, but also from a conceptual perspective. Other question?
Yeah, there are a few kind of short questions that came in the last half an hour or so. So one of them is how these equations that you're describing relate to stochastic Liouville equations, if they are related.
Well, of course, I would say they are stochastic Liouville equations. It sort of depends. I'm not sure exactly in what context that's used. The Liouville equation, you can say that the master equation is the quantum Liouville equation. It often is called the Liouville equation because it's the equation, it's the quantum generalization of, in classical mechanics, how the phase space distribution evolves. The stochastic, so there's something we might call the stochastic master equation. This stochastic master equation, which I might say a few words about in the second lecture, is if I gain partial information. So the quantum trajectory involved a perfect measurement of the environment where we extracted all of the information we possibly could, in which case, because we did that, if the state started pure, it will remain pure, but just randomly evolve. On the other hand, if I don't do a perfect measurement, for example, my detector has a finite photon counting efficiency, then I don't gain perfect information, in which case it would be stochastic, but also tracing out information that I don't have. And that stochastic master equation really is the quantum generalization of what I would call the stochastic Liouville equation.
Right. Another question, quick question is, in the Lindblad equation, whether will ignoring the L rho L dagger term, would that still give a completely positive, just not trace preserving map?
So yes, I think is the answer to that. So we know, for example, so I give you an example of this. Suppose I have, a multi-level atom. And suppose that, it's not quite exactly right, but let me just suppose the following was true. Suppose that the branching ratio of spontaneous decay from some, level F to some other level, so, F1, F2, these are hyperfine levels, such that I optically pump the system out into the other levels. In that case, I will not have those refeeding terms, those L rho, L dagger terms. They won't be refeeding. They will just decrease the population. So ignoring that would give me a non-trace preserving, but yet perfectly fine, completely positive map, which is a physical process. Okay. And in fact, that's interesting. Those of you who've never taken quantum optics with me know that it's often useful to do the master equation by just using the H effective without the refeeding terms if the refeeding is negligible.
Right. And I guess perhaps the last one for this break is, so the Kraus operators have this condition that if you sum over k dagger, you get the identity. If you do the same for the jump operators, do you obtain something similar?
Yeah, it's no, you don't, because really remember that, so we have K1 here was L dagger L dt, and K0 was 1 minus I H effective dt, where H effective was equal to H minus I L dagger L over 2 dt. Okay. So that means that K0, or maybe there's a H bar here, gosh, who knows? Yeah, is equal to 1 minus I H dt over H bar minus H bar over 2 L dagger L dt. Okay. Now, as was asked in the question, let me rotate this a different way. Come on. You can do it. So let's take a look at this. If I look at K0 dagger K0 plus K1 dagger K1, keeping terms only to order dt, I get equal to 1 minus I, yeah, all of this should be times dt. Sorry. Did I get this right? Yeah. Sorry, I've screwed this up. Excuse me. K is equal to L square root of dt. Right. So now when I add these up, I get the identity. Because K dagger K, K1, this guy is equal to L dagger L dt. So let me try to emphasize the point here. There are the Kraus operators and the jump operators, okay? The K1 was proportional to the jump operators, but the K0 is not. The K0 is here, okay? And when you write that out and I do K0 dagger K0, I get 1 minus a half L dagger L. There's no H bar there. And this plus that is 1. It's a subtle point.
All right. So what do you want to do? There are a few other questions, but I don't know, we can leave some.
Yeah, okay. So why don't we do this? I'm happy to answer questions, but you know, why don't, for those who want to break, why don't we take, what do we say here? 10-minute break. When am I supposed to quit? 2:30? No.
Are we supposed to know that, Bill? I think
Wait, no, I think, so yeah, this goes to 12.
No, 1, sorry. 1 month.
1 o'clock, yeah. Okay, so yeah, let's take a 10-minute break. We'll start at 10 to the hour, and everyone should take a nature break, and then I'll answer further questions at the end. Okay, so 10 minutes.
Sounds good.
All right. All right. Maybe we will pick up again. All right. All right. So let's just quickly review what we just had said. What we said is that we can think about the density matrix that corresponds to the state of a system, say an atom interacting with the quantized field and thus undergoing spontaneous emission, as an ensemble average over some set of quantum trajectories. And each of these trajectories evolves, this quantum trajectory is a stochastic evolution. And that stochastic evolution we can simulate with a Monte Carlo method, whereby we take a state at some time t and evolve it in some time dt, depending upon whether we have a jump, a quantum jump, which occurs with some probability p1 in some time. And if that occurs, we apply the jump operator, which is equivalent to applying the Kraus operator k1 to this state, and or no jump. If with the remaining probability, in which case we apply the no jump. And then we would renormalize and then repeat. Oops. Okay. So that's the quantum Monte Carlo method, not to be confused with quantum Monte Carlo, which is a whole nother thing that people know in condensed matter physics. This is the quantum trajectory method. Okay. Maybe I should turn this where you can see it better. Okay. All right. So I want to say something in how important of the no jump evolution. Okay. I mean, it seems like, man, if the jump didn't happen, who cares? You know, why should I even, why is that even an important thing to worry about? It seems like it's only one jump that actually the atom actually underwent spontaneous emission. So why do I even have to worry about the no jump possibility? Well, let's think about the following problem. Let's say that we started the system in a, I have to find the right spot in my notes here to make sure I'm just going to say, yeah, okay, very good. Okay, so suppose at time t equals 0, we prepared the state in a superposition of the ground and excited state. And I ask you, which I'm doing now, what is the probability of seeing a spontaneous emission in the time interval between 0 and t as t goes to infinity? So said another way, I prepared the system in the superposition of the excited state and the ground state. I'm waiting out here at my detector. And I want to wait and see, you know, what's the chance that I'm going to see a click? Click. on my detector if I wait forever? What's the chance that that happens? Please put your answer in the Q&A. I see someone was brave, and that's good. Someone said the probability, there's a chance, there's a unit probability. It's a good thought, but it's not quite correct. Anyone else have a suggestion? Anybody? Come on, folks in the Q&A, just go for it. We won't, maybe a half. Well, let me ask you a different question. Suppose the atom was in the ground state. What is the chance that I'm going to see a spontaneous emission at some point? So let me ask you that question. Suppose I started the atom in the ground state. What's the chance? Zero. Zero, indeed. Because if the atom's in the ground state, you're right. So if it's in the excited state, then the first answer was right. If the atom was in the excited state, then at some point, if I wait forever, the atom will decay. So the probability for this to be true has to be equal to the probability to be in the excited state. This is the probability that I will see a jump in that time, right? After I wait forever. But if I don't update the state, okay, so that's the probability I'll see a jump. What's the probability of not seeing a jump? The probability of not seeing a jump is 1 minus that, which is to say it's the probability it was in the ground state. So if the atom was in the ground state, we said we won't see a jump, okay? So it must be the case that a quantum trajectory, for every quantum trajectory that I do, the probability of not seeing a jump has to be the initial probability that the atom was in the ground state. As I say, the probability, if I wait forever, there should be some of the quantum trajectories, some fraction of the quantum trajectories that never see a jump if I wait forever. And the fraction of quantum trajectories which never see the jump should be this. Otherwise, I'm not simulating the right statistics. But if I don't update the state in any way, conditioned on not seeing the jump, I'll always see a jump at some point because there's always some chance the atom is in the excited state. So the no jump condition is critical to updating the state in a way that will give me the case that I should not see a jump if I wait forever with this fraction of trajectories. Let's see how that works. So let's look at this state and let's update the state after a small time interval dt. So for the no jump, if I have no jump in the small interval, then I have to apply the no jump Kraus operator, which is just H effective. Okay, and then I'm going to have to renormalize this. Okay, I'm sorry, I started at time t equals 0. So what is that? What we said is, well, I get a phase and I get a decay. Okay, so for small dt, that's equal to, oops, I'm just going to say small dt relative to, this should be dt. The spontaneous emission rate, that's 1 minus gamma dt over 2 up. All right, so now I have to renormalize. And so I'm going to get that thing in the numerator. The thing in the denominator over here is the square root of CG squared plus CE squared times the square of that, which is 1 minus gamma dt to order dt. I take the square root of all of that. Okay, everyone with me? Okay, so now to lowest order dt, I can do a Taylor series expansion of that. And what I find is that the post-measurement state conditioned on not seeing a photon is the following. I get CG times CG. Oh, I'm sorry, let me rewrite this in. Yeah. So yeah, I'm going to rewrite this in a slightly different form. I didn't do that in my notes, but I should do that. So this is CG squared is equal to 1 minus CE squared, right? So this is equal to 1 minus CE squared gamma dt. Okay, good. So now I take the square root of that and I do the Taylor series expansion, and what I get is the following. I get CG times 1 plus CE squared gamma over 2 dt times G. And when I do the algebra on the other thing with a little bit of work, not much, but I'll let you do it. I won't show all the steps along the way. What I get is this is 1 minus CG squared gamma dt times E. Okay, let's stop for a moment, pause, and look at this for a moment because it's quite important. Notice what happened. So this is the post-measurement state. Conditioned on no jump. That is to say, I didn't see a photon. So I'm looking at the atom. Hey, you atom, are you going to emit a photon? You're going to emit a photon? You're going to emit a photon? If I don't see a photon in that interval, look what happened to the state of the atom. It evolved, conditioned on my not seeing a photon. How did it evolve? I mean, of course, there's this phase, but more importantly, notice what happened. I have increased the amount of amplitude that is the atom was in the ground state, and I've taken away some of the amplitude that the atom was in the excited state. Not seeing a photon is information too. If I don't see a photon, it means, you know what? Although I don't know for sure, I should up my odds that the atom was in the ground state all along. Because if I didn't see a photon in interval, there's a slight better chance that the atom was actually in the ground state. So I should increase that by upping the amplitude a little bit in the ground state. And you know what? I got to take away some of the chance that the atom was in the excited state. Okay. And so what I see here is that if I were to do this over and over again, if I were to find the state of the system, if there was no jump in the interval 0 to t, then the state evolves according to the non-Hermitian Hamiltonian renormalized. And that is equal to that. So with that said, what is the probability of not seeing a photon in the interval 0 to t as t goes to infinity? Well, here it is. As t goes to infinity, this term goes away, and it becomes the ground state. In fact, the probability of that happening is right here, just as we predicted. So a particular quantum trajectory would look like the following. Let's say I ask, what is the probability of the atom being in the ground state as a function of time? Well, I start with some CG, and over time, the system, I would bring and break, and then maybe it jumps. And once it jumps, there's a 100% chance, right? But there are some times where I never see a jump. It would just asymptotically go there with no jumps. Those can happen too. And the fraction of the time that they happen is, as we said, this, the probability that was in the ground state all along. So interestingly, interrogating the atom and asking it, did you emit a photon? Did you emit a photon? Did you emit a photon? The more information we get that tells us we don't see a photons, the more we need to update the state to say that in fact it was in the ground state all along. All right. Any questions? All right, let me just, I'm gonna just want to show an example here. This is from the notes that are distributed.
Ivan?
So here's an example, numerical example, really beautiful.
Ivan?
Yes.
So maybe just before we move on, because there is a question which is basically asking how does this relate to the Xeno effect? Would you like to comment on that?
The Xeno effect.
Yes.
Yeah. Of course, they are related in the sense the Xeno effect is an effect which measurement affects in a substantial way the evolution of the quantum state. And the typical way the Xeno effect, as I know it, is discussed is that you start the system in some state, which is the eigenstate of some observable. If you keep measuring that observable, then if you do that measurement sufficiently rapidly, the system won't be able to evolve out of that state, even if the Hamiltonian does not commute with that observable, because you're constantly projecting the state onto this. This is a similar but different effect in that it's saying you're not doing a projective measurement, you're doing a weak measurement. So your measurement doesn't project you onto the ground state. It just weakly tells you, are you ground or excited? And with a small amplitude, you will update the state conditioned on that. But it is closely related in that measurement affects your state assignment. I want to emphasize my language here, which is the state of the system is your assignment of what you know about the system based on how it was prepared and what further measurements you have done to observe that system. And when you learn new things, you have to update your state of knowledge. So the whole Kraus operator business could be and should be thought about as the quantum generalization of Bayes' rule. Bayes' rule tells us in classical statistics how to update your probability assignment conditioned posterior to the new knowledge you gain. And you will see, if you do the problem sets, a little exercise on quantum Bayes' rule. Very good. All right. So let me continue here and just say a few words. So this, what I'm showing you here is from a very nice online textbook that you can Google by Dan Steck at the University of Oregon, who wrote this beautiful book, which is, you know, the very careful mind of Dan Steck. And one of the things that he shows here is an example of simulating the open quantum system dynamics of a driven two-level atom. So the idea is that I have a laser that is driving the system, say on resonance with some, you know, so there's some laser frequency and it has some Rabi frequency that is related to the coupling of the atom to the field. At the same time, the atom can spontaneously emit. And we know the solution to that is damped Rabi oscillations, right? What is shown here is the probability to be in the excited state as a function of time in a quantum Monte Carlo simulation. And what we see here is periods of no jump and then jumps, okay? So what's shown here, you know, the dark is one trajectory. All the things that are gray here are other trajectories. They are a random set of trajectories which randomly undergo jumps, but with exactly the right statistics that one expects because it's been simulated through the Monte Carlo algorithm as just described. And what's shown below is the ensemble average, the first line. So what it says here, the solid line is the actual evolution. That's you can solve this problem analytically and you can find the solution to the master equation in this particular case. The dashed line here is for 20 trajectory, and then the dotted line on top of that is what you get for 2000 trajectories, okay? And you see that as you have more and more trajectories, you converge ultimately to the solution of the master equation. You could put error bars on this depending on the number of trajectories and do the proper statistics. Okay, so that's a nice example. All right, let's go back to our whiteboard and let's continue. So what we just described was, we said that the solution that we wrote before, so the quantum trajectory is conditioned on a measurement record. And the evolution is what's sometimes called an unraveling of the master equation. This was a phrase that was coined by Howard Carmichael, who coined the term quantum trajectory. So a particular trajectory is an unraveling conditioned on a measurement record, okay? And then to get the unconditioned evolution, we average over those unravelings. Now, the unraveling that we got here depended upon what we measured. So in the problem that we just described with the two-level atom, what we thought about was, you know, here's my two-level atom, and what we did is that we put photon counters in 4 pi steradians all around the atom, okay? And we waited for detection, okay? And we did photon counting. So we directly counted photons, and over time, we would see some kind of click, 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 click. We would see some kind of, you know, the number of photons we would see in a given time interval would be sort of Poisson-like. And a particular quantum trajectory would depend on that particular set of clicks, which we would simulate the probability of those clicks in the way that I described, okay? But doesn't say we don't have to measure the photons this way. I mean, here we're just looking and we're here, click. Suppose that I put this photon on a beam splitter and I shove in a local oscillator as a very strong laser beam that I might describe by some coherent state with some amplitude alpha with alpha big. Then what I would see on the photodetector here would not be a set of clicks, but I would see more a photocurrent, right? With some fluctuations on it that we might say is shot noise. That shot noise would be coming from both the local oscillator, but then there would be some modification of the shot noise due to the fact that there's a signal here. The signal that I'm looking for are the photons that are emitted from this atom, which give me information about whether the atom was in the ground state or the excited state. But from the point of view of the open quantum systems dynamic, the unconditioned evolution shouldn't depend on how I measure the environment, because at the end of the day, I'm going to throw out that measurement record. But what it says is that there are different unravelings of the master equation which, when averaged, yield the same unconditioned evolution. But the back action that is conditioned on a particular measurement record will be very different, right? I mean, here I see a photon. I mean, man, that photon came from the atom. That's a ton of information. And that information is going to give me strong back action, right? It's going to project the atom onto the ground state because the photon was emitted. Here, this photocurrent, I don't know whether it's coming from the local oscillator or the signal. And so in a given time interval, there's going to be less evolution on the system. There's be less back action. But when I average over all possible measurement records that could have happened through the right Monte Carlo approach, that average will give me the same master equation. And this is a fascinating idea that in some sense, the information is in the environment, but depending upon how I obtain it, do I obtain it through direct detection or do I obtain it through homodyne detection? I will have different back action on the system and thus a different set of quantum trajectories. Okay, so I want to show you an example of that, again, from the beautiful notes of Dan Steck. So here's the same problem that we just looked at, but one in which instead of looking at the photon counts, you do homodyne. Now, of course, the Monte Carlo algorithm is quite different. Depending on how exhausted we are, I'll show you some of that to conclude the lectures. But here is a simulation of that based on the stochastic Schrodinger equation, which I'll tell you about in a moment. And you see, I mean, these trajectories are quite different. They don't have those sharp jumps into the ground state. You have a much more sort of random, fuzzy kind of diffusion, sometimes known as quantum diffusion type evolution. And it's not at all the same trajectories, but nonetheless, when averaged over all trajectories, you obtain the same damped Rabi oscillations, okay? Now, this is also both interesting from the point of view of conceptual, that you can obtain different back action on the system conditioned on different measurements that you imagine having been done on the environment. But from the numerics point of view, it's also interesting. You have to average many more of these trajectories compared to the trajectories that you do with the jump process, because each trajectory doesn't really have that much information about the jumps, okay? So it's also a choice of the unravel, if you're, from the point of view of, if you're using the quantum trajectory method for numerics, then you have to choose wisely. What unraveling would be most efficient to use to get at your system, okay? Does anybody have any questions? I'll pause there for a moment. If not, I'm going to switch back to the PowerPoint to continue that discussion. So let me share the screen there. Here it is. Very good. And let me put that into presentation mode. And let's just remind ourselves where we were here, where we were talking about this kind of measurement. This kind of measurement, I want to say again that this gives, well, in the context of where we just talked about homodyne detection, I can think about X instead of the position of the meter For those who out there who know this, I can think about it as the quadrature of the field. I'm doing a measurement of the quadrature of the field. Okay, so let's look at an example of that. Let's say that we had this wave packet centered at 0, which would be equivalent to the field prepared in the ground state of the harmonic oscillator, which is the vacuum. And the distribution of that ground state is Gaussian, okay? So we have this Gaussian fluctuation. That's my meter, which was in that wave packet state, which is equivalent to the vacuum state of the field, okay? So let's go back to what we were talking about at the beginning, where the meter's position was displaced by an amount depending on the observable I'm measuring. And I'm going to measure X, the quadrature, or equivalently, the position of the meter, okay? If I do that, I'm displacing X by an amount proportional to O. And if I look at that inner product, that's a Gaussian here, so that my Kraus operator, I want to really emphasize this, is a Gaussian. It's got Gaussian statistics, my POVM element, that is to say, which tells me the probability that I will see this measurement outcome. I'm defining the measurement outcome as just X in new units, is a Gaussian. And that Gaussian, what does that mean? It means when I apply this, I can write this in the, I could write O in the basis of its eigenvectors is this operator. Let's stare at this for a moment. What happens if chi goes to infinity? That's to say, my coupling is infinitely strong. This thing becomes a delta function, in which case that would be a projective measurement. But if its chi is finite, this is a fuzzy measurement. This is a measurement that does not project me onto a particular eigenstate, okay? So that's what I was just trying to say. So earlier, someone asked me, do I recover the standard measurement in this formalism? And the answer is yes. When the coupling is strong enough, this becomes a projective measurement, okay? But in general, it's not a projective measurement. It's a fuzzy measurement. And the reason is that there was initial uncertainty. The meter had noise in it. And the meter noise is measured by how strongly I'm coupled to the system. And so the post-measurement state will not project me onto an eigenstate. It will only partially project me depending upon the weighting that I have through this term. So let's look at this. I think it's easier to see this graphically. Let's say the initial state of the system was in some superposition of those different M states. Here's a little histogram that shows the different probabilities of the different states. And now I'm going to do a measurement. My measurement, if it is really a high resolving measurement, if the width of this Gaussian was extremely narrow, compared to this width, if my meter noise was much less than the initial projection noise of the system, then the post-measurement state would be a projective measurement. Okay. But if my meter is kind of crappy and it can't resolve which of these M states it is because this chi is not big enough, then the width is too broad. And the post-measurement state will not collapse me onto an eigenstate, but it will squeeze the uncertainty. And you will see in your homework this example. This is an example of squeezing via measurement back action. Okay, this is what we would call a weak measurement. Now, this measurement is not super duper weak. Suppose I had a crappy meter, one whose noise was so big that it can't in any way tell the difference between those things. Then it would basically do nothing. The back action on the system would be negligible. Okay. And in that case, I would do almost nothing. I would do nothing to the state at all. And I would just replace what was previously the value here of the outcome. What I would read out is basically the mean. Okay. So when I have such a weak measurement, the measurement outcome that I would see would basically be something that would look like the average value of this distribution. That's all I basically would see, with some noise, some small noise around it. Okay. So this is the case where I would have a Gaussian type of measurement that would say correspond to the homodyne detection in this problem. It would basically give me this mean value with some noise around it that has to do with the shot noise in the meter. Now, this can be formalized, and I'll maybe talk about this in the last bit in the following way. So here's an example where we want to do that. We're going to measure the system by passing a laser probe through it, and then measuring the photons that are scattered into that laser probe. That scattering of photons into the laser probe is equivalent to the kind of homodyne measurement that I described before. Okay, so I'm going to continuously monitoring these atoms by looking at the photocurrent in this laser beam, and I'll have that same kind of photocurrent that I described before. I can think about this in a quantum trajectory picture where in each time interval, a little slice of that laser beam passed through the atoms, and then I measured it. I'd see some signal that depends on the amount of time I measured, and some noise on top of that signal, which would depend on the square root of dt. And so the signal to noise I would see here would go like 1 over the square root of dt. And if I set then that, depending on the rate at which I measure, to what we said was the variance, which was 1 over that chi squared, then it's another way of rewriting my measurement signal. So this signal that I see here, this measurement signal that I see in that system would be equal to, when delta t is small enough, the mean value plus noise. And the noise here is the shot noise. Okay. Now that shot noise, we just said, was Gaussian noise. And that Gaussian noise can be modeled in this kind of stochastic way in thinking about the stochastic processes of diffusion. That is to say, a Wiener process. A Wiener process is a random walk in 1D. So what's being shown here is a random walk where I flip a coin 50-50 and the system diffuses around through that random walk, okay? The probability of having diffused away by some amount W in some time t, as we know, becomes a Gaussian. and the Gaussian spreads with a variance that is proportional to the time that I have. So this noise that I have, I don't really have time, but I just wanted to say, to give you a flavor of this, the noise that we see in the system is a Wiener process. It's Gaussian white noise. And the thing that's important about the Wiener process is that the variance of the interval is proportional to the amount of time. So the Wiener interval, its variance is dt. The RMS is the square root of dt, okay? So my measurement record that I see in this case would be the mean value plus the Gaussian white noise on top of that. And what I want to show you, just to give you a flavor of this, is how different the quantum trajectories are under this case. Maybe I should pause for a moment because I've whipped through this very quickly to see if there are any questions at this point.
Yeah, so there are two questions about whether one could have other types of noise beyond the Gaussian type of process, say correlated noise.
Yes. Well, indeed, I mean, so there's a number of different issues related to this. One thing that I completely brushed over in the description of the master equation and the Lindblad master equation is the assumptions about the nature of the environment which went into that. And in particular, the Lindblad form of the master equation assumes a so-called Markov process in which in each time interval, we completely lose information and there is no correlation between a time interval dt and another time interval dt. And so in order to do an unraveling that is consistent with the Lindblad master equation, we have to assume Markovian white noise in every interval. Now, that is not to say that one could not generalize this, and people have worked on this for many decades, to think about the evolution of a system in the context of a non-Markovian bath, an environment in which there is a finite memory and color to the noise. In that case, you would have a different kind of stochastic evolution and a different set of trajectories, but you wouldn't be able to do that in the context of the Lindblad master equation.
Got it. And the other question is about your mentioning of squeezing via measurement. Whether once you average over the measurement outcomes, do you still have squeezing?
Oh, it's a very good question. It's a very good question. So let's look at this example that we showed. So this is actually something you're going to do for homework. So someone has been present, or you looked at the homework assignment before. So here is the state, say, of the system, which might have some uncertainty, okay? And then we did the measurement. The measurement is described by this Kraus operator. This Kraus operator over here was Gaussian, okay? Now the center of that Gaussian is the measurement outcome. So the center of the Gaussian here, I should have written it, is my big scripty M, mathcal M. And oops, that is a random number. We don't know what that's going to be, okay? That is random, that happens with the probability that's given by the Born rule. But the width of the Gaussian here is deterministic. That's determined by chi, and that's determined by the length of time in which you measured the system. Now, the post-measurement state, here it goes, is here. The post-measurement state has a particular width to it, right? That width is something. It also has a center. And what is true, if you multiply this Gaussian by this Gaussian, the center of that Gaussian is determined by where this is, and the width of the new Gaussian is determined by the width of that. These two widths determine what the post-measurement state is. But since the width of this is the same in every trajectory, the amount of squeezing will be deterministic. The center of it will be random. So if I were to average this over many trajectories, what I will get is a bunch of different squeeze states, all with the same width, but centered at different places. And that would not be a squeeze state. That would be a noisy state, because the information about where the center of that state is lost. So we would have a bunch of Gaussians all with the same width, but spread out, and that would tend to actually cause this thing to decohere and spread out, because we would be adding extra noise to the system. We need to learn about the system in order to know how much we have reduced our uncertainty. Okay. Other questions? Okay. It's getting late, and I don't want to overload you with information here, but I will just say—
Ivan, can I jump in here for just a second?
Please do.
It has been suggested that people might be interested in doing a 15-minute break before.
Yeah, I think that's a good plan. I think that's a good plan. I think we've come to a good stopping point here in the 2 minutes. So let me just say, I want to just jump ahead, and I just want to say, I'll just get to this last point just to give an indication of something that is maybe just a concluding point, which is the nature of what we have learned here is that we can get different unravelings of the master equation depending upon the measurement that we imagine doing on the system. But it's also important from the point of view of the actual experiments, where I might actually do that measurement as to what is the conditioned state conditioned on the measurement record. And this kind of Wiener process corresponding to this weak measurement is a way in which we can imagine doing this kind of conditioned measurement. This is what, as the questions were suggesting, this is what is the example of what we might call the quantum equivalent of the stochastic Liouville equation, which has a piece of it that looks like the standard master equation and a stochastic piece having to do with the stochastic Wiener interval, which gives us the measurement back action. And it's through this that we can see a continuous collapse of the wave function. That squeeze state would continuously evolve and continuously get squeezed and ultimately get collapsed into a wave function. And that is what is being shown here. Here is something from a very nice paper from John Stockton out of Hideo Mabuchi's group, which shows how when you prepare a superposition of magnetic sublevels through continuous measurement, we stochastically evolve and project the wave function. So the projective measurement that we started our discussion with can be understood in continuous time. Over time, we learn more and more information, and the system will stochastically go into one of the eigenstates with the probability that's given by the initial superposition. Which one it goes to, we don't know, but each quantum trajectory is a particular realization with a final collapse of the wave function. So I think I will stop there. There's more for you to read. You can go through these notes in yourself. I'll take some final questions if there are some, and then we'll take some breaks to go. So further questions?
Right. So there were a few kind of more general questions that we left for the end. So one of them is, Anders asks, in current quantum computers, measurements are done by sending measurement signals to a device, whether that can be understood as a continuous measurement, as you've described here.
Every measurement is a continuous measurement. So, you know, when Wes measures the state of his ion in his ion trap quantum computer, the way that I guess he does it is he shines a laser beam on the atom and asks the atom, it's tuned in such a way that the atom will light up if it's in 1 and be dark if it's in 0. But you don't learn that instantaneously. You have to collect enough photons before you can tell whether you have a dark signal or a bright signal. So every measurement in the world is done in continuous time. And after some amount of time, you say, I have enough information to, for example, distinguish 0 and 1 and call that a projective measurement, but it's never perfect.
Right. Another question that was asked early on is how the theory you have described relates to measurement-based quantum computing, and how that is equivalent to the usual universal quantum computers that are circuit-based.
Yeah, well, of course, so there is an intimate relationship in the sense that the back action that we induce on one subsystem is realized by measurement on a different subsystem. And the only reason we do that measurement back action occurs is because there was entanglement between the subsystems. In this case, the two subsystems were the system and the environment. And we imagine doing a measurement on the environment, which induced back action on the system. In measurement-based quantum computing, a similar kind of thing is happening in that you've created this initial cluster state, which has entanglement between the qubits, and then you induce back action on the systems through the measurement you do on other qubits. So in that sense, they're related through that, general fact that back action on one system occurs through the measurement on the other through their entanglement.
And I guess perhaps the last question before the break is about this slide. So
yes.
In this plot, the density of trajectories, do they represent the probability of the trajectories?
Yeah, I think so. What they represent here. So in this case, there is an ensemble of some number of trajectories. The density of those trajectories tells me something about the probability of being in one of these 10 magnetic sublevels, or 9, I guess. I know this is 2. Yeah, this is 5. This is 11. This one goes to 11. Yeah. So this was an F equals 5 or J equals, no, why does it say 4? Never mind, it's 4. I don't know why, I don't remember what the heck was going on here. There are 9 sublevels because this is J equals 4, okay? But somehow, I guess through the back action, it can have more probability. It can have a bigger angular momentum through the kicks it's getting. But the density of trajectories here tells me something about the probability of being in having this projection of angular momentum. So the state that was prepared was a so-called spin coherence state, a state which had a Gaussian-like distribution of magnetic sublevels. So its most probable initial projection was 0, and it had smaller projections away from 0. So more of the trajectories land on 0 than land on 5 or -5. So the fraction of trajectories that go to a particular level is, if I had an infinite number of trajectories, would be related to the probability that it was initially in that state. It's a really beautiful paper. I encourage you to read it.
No more questions in the Q&A.
All right, everybody.
Okay, thank you so much, Ivan. So for those of you who are going to be joining for the breakout session, you can find that link, I believe, in the chat. But we're not going to start it we're going to take a little break here, at least 10 minutes, maybe 15, before we begin. All right, let's thank Ivan for a great seminar today. Thank you so much.
All right, everybody. I'm sorry if I exhausted you too much. Thanks for sticking with it. All right, take it easy. All right, guys. Thank you both for your help. Yeah,
it was great.
I think we're good. All right. I'll see you later. Oh, by the way, Pablo, I think June is gonna do the CGM today. Okay. I'm gonna be there on Zoom. All right.
Okay. Sounds good.
Okay. All right, hooray. We'll see you. I think you guys, I don't think you need to stick around for the breakout. I think that the other guys will, maybe we should go over there to see.
Yeah, maybe we'll connect to see if, I don't know if we need.
Everything is going okay.
Yeah.
I'm just heading to the breakout sessions. I'm Matteo from Underline. Hello.
Okay.
Okay.
All right. I'm gonna log off now.
Sure.
Bye-bye.
Bye-bye.